In this video I'm going to be going through bending, an introduction to bending. I'm going to be using Copeland's Engineering Studies, the Definitive Guide Volume 2. We're looking at exercise 1.6, which in the second edition is on page 24. So we're going to look using this as this simple example as our introduction to bending. But first of all, we're going to talk about what is the concept, where does bending apply, where do we never see bending. Okay, so the idea is that often we're going to have a load supported between two reactions, right? We're familiar with that. Somewhere I have a video of me setting up I don't think we'll show up on camera at this angle, but a beam, right? At this point we're familiar with beams, right? That there's a reaction on either end and we have a beam, and we've learned how to calculate reactions. Now, what we know is, so whenever we have a force being applied mid-span, we're going to have some amount of bending produced and some amount of shear being produced, right? So whenever we have a force being applied as a transverse force, right, that's perpendicular to the member, it's going to create bending and shear. Now, in trusses, we don't have bending, right? We don't get bending in trusses. We only have axial forces. We only have tension and compression. And the idea for that is that if we have our truss, I'm going to draw this really quickly, and I've talked about this in another video in much more detail. If we would apply a force, say, here, or here, what will happen then is that we will get bending and the truss will fail, because trusses are not intended, not if it's a significant force, trusses are not designed to deal with bending. So this is why when you do your assignment, it's really important that you make sure that if you're going to apply your load to the top, that your truss is designed, if it's going to be applied at the top, it needs to have supports at the top to support that weight. If it's going to be applied at the bottom, in this case, we'd have to apply the truss, we'd have to apply that load to here, because that's where the forces meet, right? There's no bending there, there's no bending in this location, because what a truss does is it takes that load and it makes them all axial loads, right? And axial loads are easier to design for. The same member can hold more load if it's only axial loads. Bending is more difficult. Also with the bending, a consideration is how long the beam is going to play a much bigger factor than it does with tension and compression. So that's the first thing we want to consider. So we now have had an idea of what bending is. Bending is created when we apply a load perpendicular to members, right, where it's a transverse force. It also, the same load case produces shear. Typically, shear is not the thing that is critical. Or almost always, shear is not the critical load case. I have, in another video I've talked about at some length about there are some cases where shear, for steel beams, shear is almost never a problem. For concrete, shear is not usually a problem because of stirrup spacing, which I've gone into in another video in a lot of detail about stirrup spacing. But for concrete slabs, shear can be a problem, and that's why we have to have shear pads to prevent the columns punching through concrete slabs. But generally, shear is not how things fail. Now, I've got another Google Classroom document which talks about how things fail in shear. That shear usually fails in a 45-degree angle. It usually fails like that. And there's video where we can see that being tested in real world, well, in laboratory conditions, I should say. Okay, so we've now given an understanding of what bending is in a general sense, and we've talked about shear, but now we're going to talk a little bit more, I'll talk a little bit more in detail about shear. So what I like to imagine is if we had a set of building blocks with letters on them, A, B, C, D, E, F, G, right, you know, like blocks with letters on them, and if I karate chop, right, that's me doing a karate chop and I go like that, it's going to knock some of the blocks to the left and some of the blocks to the right. That makes sense? Right? And so we could consider that what effectively is happening is those blocks are being forced to slide over each other in parallel layers. Right? These are in parallel layers. At that point, we have one force that's going this way, and we've got another force that's going that way. And I'm causing those blocks to slide past each other in parallel layers. Now, if I take that same concept and turn it sideways, we get the same thing. So let's imagine that they're held together with glue or something, and I have my blocks A, B, C, D, E, G, H. A bit longer this time, right? And 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. We're going to go with an even number, so we slice in the middle. Okay, I'm now going to judo chop, or, like doing my whatever. I'm going to do that here. Now in this case, you might say, well, okay, what's causing that to break? Well, part of the reason why that's breaking is that when I push down, what's going to happen is that it's going to sort of split like this. Yeah? Does that make sense? That the block will split like that? Part of what's going to happen is it's going to split like that. And we could say that if this part here is being pulled away from each other, what would we describe that force as? If we describe that force, so we glued these blocks together, and I snapped them, and I looked at the video and I saw that how it failed is that the bottom was being pulled away. What do we call pulling forces? Tension, right? So it's failing in tension. But we said that that's different, right? The tension is an axial force. Tension is when we're pulling along the beam, yet we can see that we're producing tension in this case as well. But that's more a bending consideration. I'm going to come back to that. It's going to make sense in a second. But also, we could just simply have it fail by just knocking a block out, right? That it just knocks this block from that block, right? It could just, especially if we hit D, if I hit D a little bit more, it could just knock the whole thing down, and as a result, they separate, right? They shear like a pair of scissors cutting through a piece of paper. It just separates those. When we think about paper, it's molecules, but when it's fibers, but with steel, it's molecules. But with building blocks are at atomic level, right? We're just going to say building blocks are as close as we're going to get. But so shear is when they just slide past each other, and as those layers slide past each other. Now, what's happening there is that we also, at the same time I'm applying this force, I'm also going to have reaction forces. For my judo chop, I'm also going to have a reaction force here as well. So A is actually being slid. If we're doing our judo block, the judo block might actually cause it to slide like this. Yeah, that A, because, well, that's actually not the case. So A is being slid up. Yeah? A is being slid up. So if it's going to fail, A is going to slide up. So it might be on this reaction here, it might be on a block. And when it's on that block, when I judo chop, it might just slice up. And it'll probably slice up at the same time, or it could slice up at the same time, depending on which one's stronger, A or H, that is also going to be pushed up. So what we're going to look at is we're going to try and show what's happening inside. The same way that with trusses we found the internal members. What we're going to try and do now is we're going to try and say what's going inside the member. Now the reason why that matters is we've talked before about how everything is in equilibrium, right? That when we talk about all of our equations, right, we say some of the forces are equal. If they're equal, that means it's in equilibrium, nothing's moving. So we can work out, we use that so that we can calculate unknown values. But if I had a tug of war and, well, let's say I've got 2 5-year-olds, right, and they're going to have a tug of war, and then I get 2 professional wrestlers to have a tug of war. Now, in both cases, if I have equally matched combatants, those 5-year-olds, they're pulling back and forth, right, and they're in equilibrium because their 2 forces are equally balanced, right? I guess because it's 2021, I have to make some sort of Squid Game reference here. But anyway, if I have instead 2 professional wrestlers and they're doing a tug of war, they're both pulling on the sides of the rope and they're perfectly balanced. You say, well, okay, the wrestlers and the 5-year-olds, they're both equally interesting because they're both in equilibrium. And say, yeah, they are both in equilibrium, right? Yes, in both cases the sum of the forces are equal to 0, but not if you're the rope. Right? Because if you're the rope, those 5-year-olds, it's like, oh yeah, it's not even a thing. Like, it's not even worthy of your attention. Whereas when it's wrestlers, now the rope is really like, I'm not sure if I can survive this. Right? It's possible that you could have 2 wrestlers who are so strong that they can't maintain, the rope won't maintain equilibrium, and the rope will slip, and the rope will tear. Right? Now that would be tension. But what we're looking at in this is the same concept, right? We're looking at the same concept that you can say, well, the beam's in equilibrium, right? What do I care? Why do I care what the forces are in the middle of this beam? Why we care is because we have to design the bridge to make sure that it's in equilibrium. One of the things I'm famous for saying is that in civil engineering, if it's moving, it's broken. Now, that ignores like hydrology and some other aspects, but generally, especially at HSC level, if it moves, it's broken, right? But we have to design it so it doesn't break. And to design it that it doesn't break, what that means is we have to put in enough steel, right? We have to put in a big enough member, or we might have to redesign where we put our supports, or we might have to reduce the loads that are on top, right? So make sure it doesn't break. That's the important thing here. So it's like you say, well, okay, it's in equilibrium, right? We designed it so it's in equilibrium. What's the problem? The problem is we need to make sure that this beam and these loads are such that it's not going to break. And that's what we're here to do now. Now, the first thing we want to do is we want to figure out what the maximum shear is. And in this particular case, it's super easy, right? What we can do is we can just find the reactions. So if we have a mid-load here of 40, it's symmetrical, what are our reactions going to be? It's symmetrical. There's two reactions. So it's pretty reasonable to say that reaction A is going to equal reaction B. So it's going to be, I'm not going to wait for it. I'm guessing that people just don't want to say anything on camera. Right, there are reactions. 20 kilonewtons and 20 kilonewtons on each side. Now, what we can do is we can then draw a diagram called, so what do we call this diagram? It's not a space diagram. A space diagram is where we draw the trees and the people sleeping underneath and the butterflies and everything else. What do we call this diagram where we just show the forces? Close?
Free body.
Free body diagram. Excellent, thank you very much. Free body diagram. The next one we're going to draw is a shear force diagram. Now, shear force diagrams for something like this are really simple, right? What we're going to do is we're going to say, once upon a time, there was a 20 kilonewton force, and it went up. You can all see that 20 kilonewton force. You can see where that came from, right? We started off, this is our line of 0. Once upon a time, we went up 20 kilonewtons. And then, nothing really happened, right? There was no forces until we got to the middle of the beam. And then, all of a sudden, big scary 40 went down. And then we just kept on going and going until we got to the other end of the beam and we went up 20. And you know what? It was all okay in the end. And you know what? For every shear force diagram that you ever do, it's always going to be okay in the end. We're always going to end up at 0. If you don't end up at 0, you've done something wrong. When you've calculated your reactions, if you don't end up at 0, you have done something wrong. Yeah. So, that's a pretty simple shear force diagram. We will look at a more complicated shear force diagram later, but for the moment, that's the idea. We went up 20, nothing happened. We went down 40, nothing happened. We went up 20, hey, we ended up back at 0. Nice. Now, the next thing we have to do, so if we're designing for shear for this beam, the maximum shear that we have to deal with is 20 kilonewtons. Right? That's the maximum shear that we're going to deal with for this beam. Right? You might say that there's a 40 there. It's like, no, doesn't matter. Because the maximum quantity, right, it doesn't matter if we use absolute values, right, 20. 20 is the maximum shear that we're going to do. That's what we will design our beam for. We'll say, hey, just checking, I know shear is not usually the critical value, but is shear in this case, do we have enough, is it strong enough to support 20 kilonewtons? And we say, yeah, it can. Right? So how do we do that? For concrete, we use stirrups. Right, we use vertical reinforcement called stirrups. For steel would just be, you just check, you just do a quick check to say, yep, it's fine. Because steel, shear is very rarely a problem in shear, at least in my professional experience. Okay, the next thing we're going to look at is we're going to look at bending. Now, bending is where it's at. Like, is maybe not in terms of the engineering, right, it's in terms of HSC. I like to say that I brought back bending. I'm personally claiming that I brought back bending to the HSC. But my argument is that it is the single most important thing, the most important skill for civil engineers. Right? And I'm guessing for mechanical engineers it's probably pretty relevant. Way more relevant than trusses, right, for professional working engineers. Now, to talk about bending, we're going to go back to looking at a beam and saying, okay, well, I'm applying load here, and I'm going to get some reactions. I'm not even going to worry about the load for the moment. What I'm going to say is, if I apply a load here, it makes sense that that's what how my beam will fail, right? Okay, I'm going to draw these dots. The student told me about this once. Shout out to Kaylin. Right? And okay, the dots at the top, are they closer or further away? Closer. Dots at the bottom? Okay, when things are squashed together, what do we call that?
Compression.
Yeah? So compression, and at the bottom?
Tension.
Tension. Okay, so what we know is that we have this area of compression and tension. Now, the next thing we need to look at is somewhere in the middle here, we have this line where here we have it's being squashed a lot, and here it's in maximum tension. So I'm just going to draw a diagram to show at this location, we'll give them, I'm just going to call it 1, 2, 3, 4, 5. At point 1, it is in maximum compression, right? It's in lots of compression, we're going to say. At point 5, it's in lots of tension. What do you think is happening at point 3? Nothing, right? At point 2, it's not being squashed as much as at point 1. At point 3, there is no tension or compression. I like to use the story of the Grand Old Duke of York. He had 10,000 men, he marched them up to the top of the hill, he marched them down again. When they were up, they were up. When they were down, they were down. When they were only halfway up, they were in the neutral axis and they had no force whatsoever, right? So we call this the neutral axis. Okay. Now, the idea is it's important to understand that bending. Now, at the high school level, if you don't get this, I will be honest, I did not get this until like second year uni, right? I remember really having this moment where I'm like, oh, I get it, I understand what this means now. But I'm hoping that, over 20 years that educational tools have gotten better and where it's easier to explain things than it used to be. But bending is a combination of tension at the bottom and compression. Bending is a combination of tension and compression. And what's interesting is that if we were to look at this location, the tension and compression will be less than it is here. And at this location here, it's not being bent at all. At that location, at the edge, it's 0 tension and 0 compression. So if we were to map that on a diagram, we would say, well, in the middle we have lots of tension and compression, which we're going to call bending, right? But at the other sides, we have to have 0 tension and compression, right? Because just like on this diagram here, just want to make that diagram a little bit better. Okay, just like here, we know that we have to start and finish at 0 because we said that the sum of all the forces equals 0. So let's have a look. This is, again, did not get this until 2 years out of high school, right? If you look at this section here, right, there's nothing here. So everything here, this plus this equals 0, right? So if we look at this location to the left-hand side, equals this minus this, which is 0, right? At this location, if I just pick this location, I call that A, B, and C, A is equal to C minus B, right? Or another way of saying that is if we take, let's just call this for the sake of, let's say the area of A is 1, and let's say the area of B is 1, and the area of C is 2. Let's just write that here, right? What if we could write in this situation is some of our forces, right? Shear force diagram, there's shear forces. We could say the sum of all the forces vertically equals 0. What do we have? We have A plus B plus c equals 0. 1 plus 1 minus 2. Why is it minus 2? Below the line, right? Below the line equals 0. Another way of writing that is we could say A equals C minus B, right? A equals C minus B. Yeah? So we can see that these areas, but at the edges, there's nothing for it to equal. I mean, I understood how to do the numbers, right? I could get the numbers. I just didn't understand what was going on. And there's this moment where I realized, oh, it has to be 0 at the left and at the right because there's nothing else for it to equal. To the left-hand side of this is 0, so it has to be equal. Okay, so now what we're looking at is, we know our maximum bending is in the middle because this is where we have our maximum compression, the maximum tension. The edges, there's no tension and compression, right? So it's not any bending. So this diagram is going to look like that. What we're going to do right now is we're going to prove that it looks like that. And we're going to come up with a quick way to get what is the maximum values, right? Because what we're really interested in is this peak. Now, if you've done calculus, you might be, or integration, right? You might be interested in the idea that maximums happen where the integral, or relative to the derivative, depending on your point of view, right? Where we cross the x-axis is where we get our maximums. So here we've crossed the x-axis, that's where we've got our maximum, right? These things are related, right? So where we cross the x-axis is where we're going to get our maximums. So what is our maximum here? Well, in this case, when we have a simple, so it means we only have 2 reactions. We don't have like 5 or 6 reactions, right? We don't do that in high school. In high school, it only could be 2 reactions, or it has to be fixed. It has to be a pin and a roller, or it has to be fixed. That's it. That's the only thing they're allowed to do in high school. At uni, yeah, you can have 5 or 6 reactions for, like, you know, you've seen bridges that have 5 or 6, you know, pillars in the middle, right? Supports in the middle. So it's simple. Everything we do in high school is going to be simple. It's symmetrical, and with only one load, we can use this formula to calculate this value. We can say M max, which is what we're finding, the maximum bending moment. So we've got the bending moment diagram. The maximum bending moment is equal to FL on 4, right? You just use this all the time, right? Now, a lot of the time people use PL on 4. We can use FL on 4 because we don't remember that it's forces. The reason why people use P, sometimes they call this FP, is for point, to say it's a point load, right? It's a single load in the middle, it's a point load. Now, if we type that in, so we want to make sure that we're using newtons, and I like to use millimeters, but for the moment we're just going to say 40, right, times 2 divided by 4 is going to give us 20 kilonewton meters, right? I haven't checked this, so are we really embarrassed if that's wrong? Oh, I had a sense that was wrong. Okay, our L, here we go. L is this distance. L is this distance. L is the distance from one side to the other. So we had 2 plus 2, so what's our L? 4. Sorry, I hate that people use pen that they have to replace things. Who knows? Will I do an edit? Almost certainly not, because I'm incredibly lazy. But if I was to do an edit, let's go through it from the beginning. So we're going to use this formula. FL on 4, F equals 40 times L is 4. 2 plus 2 equals 4. Divided by 4, crossing out gives us 40 kilonewton meters. Sometimes there's an advantage in having done this more than once. You kind of have a sense of like, no, that doesn't feel right. Okay, so that's our maximum bending moment. Now, I like to convert it, but we're not going to worry about that for a moment. Now, here's what I'm going to do. I'm going to prove to you that it is in fact a triangle, and I'm going to prove that we get to this point. So, see how I've labelled this point here 1 and point 2? And we're going to call this point in the middle M. I'm not going to do the edges, right? I have done that in another video. I'm going to try and go through this quickly and say, let's prove point 1 and point 2 and the maximum. What we're going to say is, the force on the left-hand side, we're going to start with 1. The force, the sum of the moments are equal at every single location. We've proven that. We've talked about with reactions. The reason why we like to take reactions from the edges is because we have two unknowns, and by taking, we can choose any location. We just choose one of the unknowns to eliminate an unknown. But at every single location on this beam, we can take the sum of the moments and have it equal 0. What that means is the moments to the left-hand side have to add up with the right-hand side to 0. Right? So if this is minus 10, that side will have to be plus 10. If this side is, as an example, right? If this side is minus a trillion, this side will have to be plus a trillion. When we say plus or minus, how do things get be plus or minus? When we talk about moments, what do we set as a positive convention? Clockwise, exactly right. So here's what we're going to do. We're going to say, at the sum of the moments at location 1 equals 0, setting clockwise as positive. So what we're going to say is 0 equals the left-hand side plus the right-hand side. Yeah, from left. So what does the left-hand side look like? Well, the left-hand side looks like this. It has a reaction force of 20 kilonewtons going up, and then it has the rest of it. So how far is it? It's 1 meter. Okay, so its force, if we're putting our pin at location 1, and we're going to rotate it, which way are we going to go? What is it?
Clockwise.
Yeah, clockwise. What's its value?
Oh, positive.
Yeah, positive, but it's the magnitude is force times displacement, force times perpendicular distance is force times perpendicular distance is 20. Exactly right. Okay, 20 kilonewton meters clockwise. Right. Now the other side of this beam looks like this. We have a force, a big force of 40, and then out here we have a smaller force of 20. Right. That's what our beam looks like there. What are our distances? Well, this is 1 meter, and that's 2 meters. Okay, so let's type in our forces. So we get 0, so RHS equals, we've got 40. How far away is 40? What's its distance? From location 1. 1 meter, exactly right. So 40 times 1, and then, is it going clockwise or anti-clockwise? Okay. And then what's this distance? What's this? What about this one? The force is 20? What's the distance? Actually, this distance is 1 plus, so it's 1 meter to the middle, and then 2, right? So this is actually what distance?
It's not 3.
It's a 3, yeah, okay. Sorry about that. Sorry to anyone who's used pen already. Okay, so it's 3 meters away, yeah? Clockwise, anti-clockwise? We're going to leave it as negative, and we'll say, so what is our answer? We're going to have 40 minus 3 times 20 is? Yeah, so minus 60. 40 minus 60 is? Negative 20 kilonewton meters. Now, we can write 20 kilonewton meters anti-clockwise. Yeah? And then if we have LHS plus RHS equals 0, what we have is 20 plus minus 20 equals 0. So what is our value at this location? At this location it is? Just worked it out. No. If we measure, yes, it's 0. In the tug of war, right, it's 0. It's not moving, right? It's not interesting, right? The wrestlers, the 5-year-olds, it's all the same. Not to the rope. In this case, not to the beam. You say, yes, it's 0. 20 plus 20 is 0. What's a big? It's 0, right? It's not uninteresting. Not to the beam. To the beam, it is interesting. The beam is having to deal with 20 on the left and 20 on the right. So what quantity do we write down? 20 kilonewton meters. Yeah, that is the moment at that location, is 20 kilonewton meters. Yes, it's true that the sum of the moments is 0, but what we're saying is the left hand is 20 and the right hand is 20, right? That when we have the beam, the amount that it's being squashed is 20 kilonewton meters at the top and 20 kilonewtons at the bottom. Stretch 20 kilonewton meters at the bottom. Okay. Based on the time, I can see I don't have time to do point 3. Point 2. I'm going to say that the textbook has the answer. You can have a look at it, and it's pretty self-explanatory. When you actually work it out, it's a symmetrical thing. Also, it makes sense that this line is linear, right? It also makes sense from a calculus point of view that this line would be linear. What is more interesting is we're going to find the maximum bending moment using this same method, right? So what we're going to say is the sum of the moments at M, which could be for mid or for maximum, is 0. We've said clockwise is positive. What is our drawing? On our left-hand side, what do we have? On our left-hand side, we have a reaction of 20, and then we have our force. I'm actually going to use the colours this time because I think it's really important to see the colours this time around. Right? What we have this time is we have our beam and we have 40 kilonewtons down, and then on the other side, we have a reaction of 20 kilonewtons up. That's our left-hand side, right? You're happy with that? Okay. So, what's the forces we're going to write down in this diagram? So, left-hand side is going to equal what? What are the forces? We'll start here. Yeah? And we're taking moments about M. Remember, we're taking moments about M. So, we have 20 kilonewtons. How far away is it? How far away is it? 2 meters, exactly right. And then we have 40. How far away is 40?
0.
Just on fire this week. Absolutely on fire. It is 0. I was hoping someone would say 2, so I could say, no, not 2. But you got there, right? You just jumped in there and Okay, so what we're going to have, that's going to be equal to 40 minus 0 equals 40. And it's positive, so we're going to say 40 kilonewton meters clockwise. That's the left-hand side. The right-hand side is going to be, let's have a look. I could have left the diagram there, but I thought I'd better to draw it again. I lost a lid yesterday. Who knows what happened to that poor pen? I gave it to Mr. Short because I couldn't bear to deal with it, this pen that was going to die on me. Okay. Let's go through this one. So measuring from M, we've got 40. What's the distance?
0.
Okay, and then we've got this 20, right? Is it going clockwise or anti-clockwise?
Anti-clockwise.
How far away is it? What's the distance?
2.
So we're going to get 0 minus 40, which is going to equal 40 kilonewton meters anti-clockwise. You guys have got this, right? Yeah, you got this. I'm just so impressed with this class. You're just doing really well. So, we can use this formula, FL on 4, right? Occasionally people do silly mistakes like they use 2 instead of 4, right? But we can use that formula. But that formula only works in a very, very specific circumstance, right? Where we have a symmetrical force, a symmetrical loading with the force in the middle, right? Now, I think it's useful, right? All the time. In my professional life, I use that formula all the time. I never drew these diagrams, right? Professionally. Oh, well, very rarely. Not for something like this, right? I would just say, oh, I know what it is. I don't just calculate. But we have to be able to, we need to be able to produce these diagrams. Why do we need to be able to produce these diagrams? So we know how much reinforcing goes in the concrete, right? To make sure that the steel is strong enough. So if we say, look, the steel, we have to use this size steel. We've been told by the client we have to use this size steel. We say in that case, you need to put the load somewhere else because you need to have another support, right? You need to change the load condition because otherwise this is going to be unsafe, right? And you can say, oh, but it's always equals 0. 40 plus 40 equals 0, right? 40 minus 40 equals 0. Yes, our job is to make sure it equals 0 because if it doesn't equal 0, someone is going to get killed. Right? That's our job, is to make sure that we design for this maximum bending moment. Now later we'll find out how we can calculate bending stress. Now I'm going to say this as expecting the bell to go any second, that bending stress is different to the regular stress formula. I have said that in this subject there's one thing you need, the second most important thing you need to know is that stress equals force over area. Stress equals force over area, unless it's bending stress, in which case it's mi over I. Yeah? So that's where I'm going to leave it, and I'm going to say this letter M is that value. That's where this comes from. Right? This value, it goes into that letter M. And Y, the last thing I'm going to say, Y, remember how we had the maximum tension and the maximum compression in this distance from the neutral axis? The Y is this value. That is the Y. If it's symmetrical, it doesn't matter which Y you use. If it's not symmetrical, it depends. Are they asking for compression or are they asking for tension? If they're not asking for either and it's not symmetrical, you should use big Y!